All right, let's just go ahead and keep working with the appliance stored data and the matrix representation. Just remember, this is a 5 observation data set only meant for you to understand the concepts in a little easier way. So let me go ahead and use the code that we used last time. We have the y vector here. It's a column vector, 5 observations, 1 column. So we also coded the x or the design matrix x by placing ones on the first column and then the values of x on the second column. We were then obtained the parameter estimates for the least squares method. What we basically did was we got first the x transpose x matrix by using this line of code here. And we got the determinant, which in this particular example, the simple linear regression, that determinant was equal to 50. Now remember, the determinant is data dependent, so you would not know when is a determinant actually bad or close to zero or not. You would have to compare it to something else. Um, we also got the inverse, and remember the inverse of a matrix is obtained using the solve function in R. So we are going to go ahead and actually get the inverse, and this is what we get for the inverse of x transpose x. We got also x transpose y, and then finally we got the parameter estimates. The parameter estimates came out to be minus 0.1, 0.7 on the slope. So again, if we did that using the LM function, we will just go ahead and get sales and advertising. We are gonna put that into a data frame, and again, this step is only for practicing putting things in data frames. We could get the regression without having to use that in the data part of the LM function. But let's just do it that way for consistency. So we get that regression, and again, we have now the parameter estimates, which are exactly the same as what we got in these B parameter estimates vector. And we have here the ANOVA as well, analysis of variance. So we can see that MSE is 0.36. That's an estimate of the variance around that regression line. So if we plot this, so let's start by again making a scatter plot of sales versus advertising. So let's just put it this way, of sales versus advertising, and we're gonna use the plot function, and again using the x variable first, and again the y variable later. So let's just get that plot here. Alright, so let's put some limits on the y-axis here. And again, I'll show you later on why we want to do that. So let's let it go from -2 to, let's say, 6. And let's rerun that. Right, so we have here, we can see the relationship between the variables. I'm going to use the upline function to plot my regression 1, and I'm going to color it to be red so that we can see that relationship. Again, we can see a positive relationship, meaning as advertising increases, so does the sales, and that's what's expected. Now, bear that in mind when we go ahead and get the example from the other predictor, let's say advertising 2, that we practiced. So let's just go ahead and get that advertising 2 coded. So I'm just going to go ahead and put it here. So I'm going to say advertising 2 is equal to, and we're just going to concatenate the values that we put in the example, 2.1, 3.9, 6.3, and then we said the next one was 7.9, and then finally 10. Now, this advertising 2 is very related to advertising. It's just a multiple plus some error. So if I actually had plotted advertising versus advertising 2, again, let me just use the right variable names. What you would find is that they almost fall in a perfect line. So they are very related. Okay. Um, we are also going to have another variable in, and that is the variable month, which you will see that month is exactly the same as advertising expenditure. So let's put it in there so that we can see what goes on. So it's 1, 2, 3, 4, and 5. And then let's just create another um, predictor, and let's suppose that that predictor is not very related to any of the predictors that we have, and let's call it, let's say this is market share or something like this, and let's say that's the share of the market of that particular product. So let's say it's 10%. Let's say on the second one is 15, and then it goes back to 10. Let's say 9, and let's say 17. So probably not a very good predictor of sales, because it behaves completely sometimes opposite of what sales does. But let's see, let's check how these three predictors um, behave. So let's add it to the appliance data. So I'm gonna do the data frame function, and then basically I'm gonna paste the cells there. I'm gonna put advertising, advertising 2, the month, and finally the market share. So so we have those three. Now we have four possible predictors. Okay, so I'm just gonna go ahead and put everything the whole screen now so that we can better visualize it. Okay, so now let's take a look at what happens when you have the advertising and the advertising 2 in just a single regression. All right, so say let's predict sales with advertising and advertising 2. Now remember, these two predictors are very related, almost multiples of one another. So I'm gonna just do the design matrix, and that would be, I'm just gonna say, let me copy and paste this from above here, and what I'm gonna do is put exactly these values, and at the end of the concatenate function I'm just gonna add advertising to the object. So what that would do is do everything that we did before plus the object advertising 2, and then I'm gonna say now the number of columns is equal to 3. That should be enough. Okay, so let's see if it worked. Now you can see that we have a column of ones representing the y-intercept, the column of advertising, which is the value, and then advertising 2, which is very related to advertising. All right, we have already coded the y vector, so we have it up here, so it would be the matrix with one column, so we don't need to put that back one more time. So let's go ahead and get the parameter estimates. Okay, so the parameter estimates is going to be based on the x transpose x inverse matrix and the x transpose x y matrix as well. So let's take a look at the x transpose x matrix. So let's code it in transpose of x multiplied by x, and let's see what we have. So what we can see is that the matrix is 3 by 3 as expected. Now, because these two columns, the advertising and the advertising 2, are very related, now the determinant is going to be lower. I mean, it's going to come down to almost 0 because of the what we call collinearity between these two predictors. But let's check it out. So we are going to say determinant of x transpose x, and let's run that, and we can see that this is 5.4. Again, it's very units. It depends on the units of the problem. So I'm just gonna say that if we compare it to the original determinant using advertising, which is equal to 50, this is a lot lower than that. So you can expect that because these two columns are very related. So let's get the inverse of x transpose x. I'm gonna do this with the solve function again. Is solve of x transpose x. And right now I'm just gonna go ahead and get that inverse right there. You can see that there is some sort of um, covariance between those values in there, between the variable advertising and the advertising squared. All right, so now we can go ahead and get the x transpose y, put it in, so that would be transpose of x multiplied by y. So these would get us the x transpose y matrix, which is actually a vector, column vector. And then we can get finally the parameter estimates b, which is going to have exactly the same formula as before. So that's the nice thing of using matrix notation, is that the formulas never change. They stay the same regardless of the number of predictors that you have. So now the parameter estimates are going to be minus 0.2, minus 0.1, and 1.29. This is the estimate of the slope. This is the estimate. This is the first one is the estimate of the y-intercept, the estimate of the slope of variable 1, and the estimate of the slope of variable 2. Something to note here is why the slope for advertising is suddenly negative. This doesn't look like a negative slope. It looks like it's trending upwards, right? And the reason for that is because of the multicollinearity present in the dataset. The variances in the estimates are, sort of biased. And I don't want to call it exactly biased because that's a statistical term, but what I want to say is that there is some variation on those estimates, which make it not reliable enough, right? And remember, so let's go ahead and let's just go ahead and code it into the LM function. And again, remember that we are gonna use exclusively the LM function to get our regression estimates, and we're not going to use these matrix notation, but it is important to note what goes on the background. So we're going to say LM function of, so we're going to use LM to produce the multiple linear regression. So I'm going to say here, let's call it regression 2. And I'm going to use a LM function with sales as a predictor of, and then I'm going to use advertising plus advertising 2. That's the way we add more than one predictor in a regression. So I'm going to say data is equal to, and I'm just going to use the appliance data. Summary of regression 2, and I'm going to get also the ANOVA so that we can see a few important statistics. All right. And yes, we get a slope that is negative, just exactly as the parameter estimates. So again, this vector b is using that inverse of x transpose x, which we said that is sort of, the determinant has a lot to do with that inverse. It's calculated using that determinant, and that determinant is close to 0. And when you divide something by a number that is close to 0, you get that value inflated. Um, so in other words, the estimate, the variance of the parameter estimates is given by MSE, which is this value that you see right here, mean squared residuals, multiplied by actually X transpose X inverse. So we can get that. So we can say variance of B is equal to, well, we can just go ahead and paste that exact number right there. And that's going to be multiplied um, by, and again, this is a scalar number. A scalar means it's just a number multiplied by the matrix, and when you multiply the single number by a matrix, it's just multiplying every single element by that number. So let's just go ahead and get that, and I'm going to show you what that variance of B is, and the variance of B is just going to be those values right there on the diagonal. Okay, so if you want to see it just the diagonal values in the matrix, you can use the diag function. So let me just put it here. Diag function gets the only the diagonal values. So I'm just gonna do this. Let's call it variance of B so that it is easier to understand. I'm just gonna say that this is the diagonals of that bar matrix. Okay, so that is the variance of B. So if I wanted to get this the standard error of B, I would just get that square root of that particular vector right there. So if I do that, I can get the standard errors of B. And I can see these are the standard errors of B, which will correspond actually to the standard errors that you see right there, the 0.74, 4.08, and 2.06. So that's a way our on the background gets those those estimates of those variances. Now what I'm trying to get with this is that the inverse of X transpose X is here getting these parameter estimates, but it's also here on the variance. So if you have something, an estimate that is sort of not reliable, because there's a lot of variation in that parameter, and the same thing with the standard error of that estimate, then when you get the t statistic, that is also not going to be reliable. And also the p-value as well. So what this regression is telling you is that neither advertising nor advertising 2 are good predictors or linearly related to sales. But wait a second, doesn't that look like there is some sort of linear positive relationship? Didn't we do this regression 1 and we found that it was the advertising variable by itself was significant? I mean, if we just do the summary of regression 1, this is what we saw before, we found that it is significant at a 5% alpha level. But all of a sudden, this no longer becomes significant when we include that advertising 2 variable. So it made both advertising and advertising 2 be insignificant. And the reason for that is because this value right here is inflated, and this parameter estimate sort of is inflated as well. So that is a problem that multicollinearity causes. It causes the variables to be inflated. So we have to be on the lookout for that. All right. So I'm going to show you later the steps that we take in order to make sure that we don't have this problem. But for now, let's just keep on, and then let's do another regression. And let's not code the thing in a matrix notation. Let's just get it exactly from the LM function. So I'm just gonna say, let's create a model using, let's predict sales using now advertising, and month. Now the thing is that this is even worse, because if you remember from this, month is just exactly the same as advertising expenditure. So it's actually a linear comment, not, it's just a multiple. Multiply that column by 1. So let's just go ahead and see what happens. We're going to get here, let's call it regression 3, and I'm going to get a linear model using cells and using now advertising as a predictor, and then we're going to use month as a predictor, and we're going to use the appliance data. And we're going to get the summary of this regression model 3, and we're going to get also the ANOVA for that regression model 3. So let's just go ahead and get that. And what you will find is that the output, you receive the output, you get an output, but hidden in here, well, not exactly hidden, but at least as maybe Arsh telling you, there are some singularities. One of the parameters is not defined because there are singularities in your X transpose X matrix. It doesn't exactly say that, but that's what it means. So you will get some NA values. This is a problem that many people receive in their regressions, and they don't know where these problems come from. And this is actually more common than what it appears. And specifically, the reason for that is most of the times when you're coding dummy variables, which we will see later on. But for now, when we see something like this, an NA in an estimate, that means that that X transpose X matrix was not invertible, or the determinant was 0. We couldn't get that inverse. And let me show you something else. So from this model, I don't have the model matrix, or again the design matrix. I'm able to get that using the function model.matrix. So if I say model.matrix of regression 3, if you see that, that tells you what is the model matrix that we use. We can see the intercept, the advertising, and the month. So we don't actually have to just code it in by ourselves. It's already there in the model if we wanted to get it. So let's place it into an X, let's just name it X. So we have the X matrix now. And let's get the X transpose X matrix. So we're going to say transpose of X multiplied by X, and this is our X transpose X matrix now. We can get it here, but what do you think the determinant of that matrix is? Well, I can't hear you, but I'm guessing you said it's gonna be 0 because these two columns are exactly the same. So if we're gonna get the inverse of that matrix, X transpose X, I'm gonna get an error saying that the system is singular, meaning that there is a singularity in that. This is exactly two columns that are exactly the same. All right, but I want to point out for now these output where you get NAs in the estimates, the standard errors, t statistics, and everything. And well, ours meant mostly for people who kind of understand a little about matrix notation. So it's basically telling you because of singularities in your data, it is not able to calculate that specific estimate. And it's up to the analysts just to understand what's going on the background. It's just that one column is either multiple or an exact or a linear combination of another column. All right, so if finally let's do a third model. Let's do predict sales using now advertising and another column, and we called it market share. Okay, so now we are expecting this not to be too related, these predictors. So in this case, let's call it regression 4. I'm gonna use an LM here using sales, and then using advertising as a predictor, and then I'm just gonna use market share as another predictor, And I'm just gonna say this is the data appliance, and I'm gonna get the summary for those two. So I'm just gonna reuse some code here so that we can see the parameter estimates. And now we can see that sort of the estimates are now positive for advertising and market share. The p-values did change. In the presence of each other, they don't seem like together they do predict sales very well. So those are things that you need at least to recognize when you have more than one variable in the model. It means that together they might or might not do a good job predicting the y variable. But that's what I wanted to illustrate. This is a very important problem in regression. Be able to recognize when two predictor variables are related. And remember, we call that multicollinearity. So we're going to go and talk a little bit more how to recognize when there is multicollinearity in the next set of videos. But for now, let's just stop it there, and we'll see you later.